Good morning. This is Ankush Chakrabarty. I'm a research scientist at Mitsubishi Electric Research Labs, and today I'm here to talk to you about learning disagreement regions with deep neural networks for reducing the practical complexity of mixed integer MPC.
Model predictive control is a powerful control algorithm that's been widely implemented in industry for applications which require optimal performance with constraint enforcement. Mixed integer MPC or MIMPC for hyperdynamical systems need to solve a mixed integer quadratic program at every time sample. Even though there are exact optimization algorithms that rely on branching bound for solving MIQP, and these have fast variants and modifications and can be implemented with powerful software tools like Gurobi, the main drawback is that MIQP problems are still NP-hard and require significant computational effort. While there are heuristics that can be used to quickly find feasible solutions instead of exact solutions like rounding schemes, feasibility pumps, and more recently machine learning, we want to use these heuristic techniques when possible and rely on exact solvers when necessary. So we assume we have two solvers, a strong solver which is expensive and exact, and a weak solver which is cheap and typically suboptimal based on heuristics. So we can reduce the dependency on the strong solver of the MIMPC online if we know where the strong and the weak solver disagree. Within the disagreement region, for safety and exactness, we call the strong solver, otherwise we use the weak solver. The smaller the disagreement region, the fewer times the strong solver needs to be called, and this results in a reduction of practical complexity. However, these disagreement regions are difficult to compute analytically and exhibit complex geometries, which is why in this paper, we propose the use of deep neural networks in order to obtain these disagreement regions and use it to reduce the practical complexity of MIMPC online. This is a typical MIQP formulation for mixed integer MPC for linear systems. We have an objective function which has a stage cost and a terminal cost, both of which have linear and quadratic components. We have an initial state, affine state dynamics, and bounds on the measured outputs. We also have integer bounds on the controlled actions and a terminal constraint. Our strong solver is based on an exact branching bound algorithm with advanced pre-solved branching and cutting plane techniques for efficiency. And our weak solver is based on relaxing the MIMPC problem, as you can see in the shaded area. Instead of having integer control actions for all n steps, we pick some m, which is much smaller than n, and only constrain those m steps to be integers. The others can all be real valued. There are some interesting properties that arise from this formulation. For example, the first control action is still going to be an integer. Any feasible solution to the exact MIQP is a feasible solution to the relaxed one. And therefore, we believe using the weak solver should result in acceptable performance, at least for some of the initial states due to state feedback. In order to define a disagreement region, we have to first define what we mean by disagreement. And we define that through the use of closed loop trajectories using MIMPC. We have two policies, one which uses the strong solver and the other which uses the weak, and they result in corresponding closed loop trajectories, Ψ(s) or Ψw. Any closed loop trajectory is considered feasible if all the constraints are enforced at all points of time. Concept of feasibility lends itself to disagreement, and we can define a partition of the state space based on this disagreement definition. So an infeasible region is where the closed loop trajectory is generated by the strong solver is infeasible. The disagreement region is when the strong solver generates feasible trajectories, but the weak solver cannot. And if both the weak and the strong solver generate feasible closed loop trajectories, we call that the agreement region. In order to perform disagreement learning, we have to do some steps offline. Specifically, we need to collect data. So we begin by sampling initial conditions x hat 0 from the admissible state space. We obtain both the weak and the strong closed loop trajectories, by which I mean closed loop trajectories based on the strong and weak solvers, according to which we can check our definitions of infeasibility, disagreement, and agreement, with which we can obtain a unique label for each initial condition. And that label is either it's in the agreement region, the disagreement region, or it's infeasible. So after we've collected all of this training data, we can use it for the disagreement learning network, or DISNet, by passing through an initial condition x hat 0, and trying to predict in which region the agreement, disagreement are infeasible that x hat 0 will lie. And we can use this online for the FPC. For training the DISNet, we use a cost-sensitive categorical cross-entropy function as the training loss. This is because we want to bias misclassifications. We prefer to make mistakes in some directions more than others. For example, if the initial state is actually a disagreement label, but it's misclassified as an agreement, this case is more harmful and needs to be penalized more than if an agreement label is misclassified as disagreement. This is because if it's an agreement label, which means it belongs to the agreement region, but is predicted to be disagreement, it'll just call the strong solver, which is safe because we still get a feasible solution, but it's wasteful because we could have worked with the weak solver. However, if a really disagreement label is predicted to be agreement label, then it calls the weak solver, which cannot necessarily find a feasible closed loop trajectory and could result in constraint violations. Similar asymmetry also occurs between disagreement regions and the infeasible regions. Therefore, we want to bias DisNet to misclassify in safer directions. Let's look at how DisNet is used in the MPC loop online for solver selection. So given a current state xt, we query DisNet to understand which region it belongs to. Accordingly, the strong or weak solver is called, and a sequence of control actions is computed for the prediction horizon length n, after which we only implement the first control action, just like an MPC. So the proposed law looks something like this. If the label is agreement, we call the weak solver. If it's in the disagreement region, we call the strong solver. If it's infeasible, we call the strong solver, or we use some fail-safe mechanism. Note that this control law actually comes with a guarantee, and the smaller the volume of the disagreement region, the more the potential speed up of online MIMPC, because we're depending more on the weak solver than the strong. We also provide in the paper, under idealized learnability conditions, how to get recursive feasibility and asymptotic stability of the MIMPC with the DisNet in the loop. We test the potential of our DisNet and MIMPC approach using a real-world example of a satellite in a station keeping problem. So this is a satellite in a low Earth orbit, which is being pushed around due to third-body gravity, drag, and solar pressure, etc. And the MPC's objective is to maintain it within the station-keeping window on the bottom right figure between -100 and 100. We assume simplified system dynamics, and we have control inputs that are a mix of binary and continuous variables. So the final MPC problem needs to solve MIQP programming problems. We have an LQR-like quadratic cost with the following constraints on the state, as well as on the control input. In this slide, we present some results on disagreement learning. DisNet takes the 4-dimensional state vector of the satellite position and velocity as the input and predicts a label based on the agreement, disagreement, and infeasible regions. Here are some details about the architecture. This is a deep neural network, and we use atom optimization with the cross-entropy loss that we discussed before. We have a weight on that loss, which is 10 times higher for the logic corresponding to the disagreement region for safety considerations. So our data set for training is of 75,000 unique labeled samples drawn randomly from the admissible state space, of which 20% are used for validation. And because only a few of these samples lie in the disagreement region, we have to counteract this imbalance by employing a weighted sampler in the mini batch. The results of training you can see is on the figures to the right. So the bottom figure is actually an instance or a slice of the disagreement, agreement, and infeasible regions for 0 velocity. The blue is the agreement, the light color is the disagreement, and the green is the infeasible region. Overall, we show in the confusion matrix with 100,000 testing samples, which are different to the training data, that the accuracy is pretty high. So the bottom right element is 94.61% accuracy, which is good. And most misclassification is done on the disagreement region, but it's been biased using this const-sensitive loss, as we've discussed before, for safety. In order to understand how the DisNet in the loop with the MIMPC works in closed loop, we test 1,000 simulations from 1,000 different initial conditions, and we test for a time duration of 1,000 time steps. And the median of the exact MIMPC simulation time is about 32 seconds over these 1,000 solver calls. As you can see on the bottom left figure, if you use exact solvers, whereas our proposed method actually reduces that by about 70%. This is especially relevant in space applications where power needs to be saved as much as possible. So savings can increase even further in the cases when the satellite actually enters an agreement region and remains there, but that is not always the case. So the bottom right figure actually shows that even though we start from an initial condition that requires an exact solver and move into the agreement region, switching to the weak solver, there is switching back and forth even later on, as you can see with the blue stars and the red circles interspersing towards the middle of the figure. This is because the disagreement region and the agreement region is changing with different velocities. The middle figure is just a slice for zero velocity. And therefore, it's quite a complex decision boundary between the agreement and disagreement regions. This further corroborates why we need deep neural networks to represent these regions. To summarize, we propose an algorithm for reducing the practical complexity of mixed integer MPC by partitioning the admissible state space into regions where an exact solver can be replaced by a faster suboptimal solver using heuristics. This replacement is done cautiously so that we can avoid constraint violations online. In particular, we propose a deep neural line via simulations to characterize the partitioning of the state space into subregions. It is queried online to decide when to employ the strong or weak solver, and it's trained with an asymmetric loss function so that we can promote safety. We also provide in the paper preliminary theoretical guarantees and empirical results that show the potential of this method. Thank you for listening.